Hey everyone! In this video, we're going to learn about normal forces. We'll start by explaining what causes a normal force. Then we'll explain what the word normal actually means. After that, we'll see how the magnitude of a normal force can change based on the other forces involved. We'll also talk about how to draw a normal force in a free body diagram. At the end, we'll walk through a few example questions. So, what is a normal force? If we drop a book, we know that gravity is going to cause it to fall down. But if we place a book on a table, why doesn't it fall through the table? The force of gravity is still pulling it down, so if the book doesn't move, there must be another force on the book that's acting upwards. And there is. There's a force from the table that is pushing up on the book. This force exists because the book and the table are in contact with each other. There's a few different names for this type of force, like a contact force or a reaction force. But we're going to call this a normal force, and we'll label it as Fn. We'll talk more about this in a minute, but the word normal just means perpendicular, and we call this a normal force because its direction is perpendicular to the surface of the table. So this is just the force acting on the book from the table because they're in contact. And we learned in the last video, on Newton's third law, that the book must also be exerting a downwards force on the table with the same magnitude. But what actually causes a normal force, or a contact force, and why don't objects move through each other? It may look like this book is touching the table, but let's zoom in and look at these two objects at the atomic level. All objects are made of atoms, which consist of particles called protons, neutrons, and electrons. Electrons are negatively charged, and two particles with the same charge repel each other. So the electrons in the book and the electrons in the table repel each other with equal and opposite electric forces. And the two objects are not actually touching at this scale. This is similar to how the same poles of two magnets repel each other with magnetic forces. It's almost like there are a bunch of tiny springs between the electrons of each object, pushing them apart. So the normal force acting upwards on the book is all of the electric forces on the book's electrons added together. And the same is true for the normal force acting downwards on the table. So, if you try pushing the book into the table pushes back with an equal and opposite force. Now let's talk about the word normal in normal force. Normal means perpendicular, and a normal force is always perpendicular to a surface. So the normal force acting on this block is perpendicular to the ground. That means the angle between the normal force and the ground is a right angle, or 90 degrees. If we held a book against a wall, the normal force on the book would be perpendicular to the wall. The normal force acting on this block is perpendicular to the surface of the ramp. As this car drives over a hill, the normal force on the car is always perpendicular to the road at that point. And if a ball is rolling around the inside of a circular track, the normal force on the ball is always perpendicular to the track. One of the interesting things about a normal force is that it changes magnitude based on the other forces that are involved. Let's say a person is pushing this block against a wall. The block and the wall exert equal and opposite normal forces on each other. Let's say they're pushing on each other with 10 newtons of force. If the person pushes harder on the block, then the block pushes harder on the wall, and the wall pushes harder on the block. The magnitudes of these normal forces get bigger. But unless we have an object that's flexible, we can't really see this normal force changing. One thing we can do is insert a scale between the two objects. This will measure the normal force between the block and the wall. So now, when the person exerts more or less force on the block, we can see the normal force is changing. Another thing we can do is imagine there are springs between the two objects. When you push on a spring, it gets shorter, so that would give us a visual indication that the normal force between the block and the wall is changing. This is basically what's happening between the electrons in the block and the electrons in the wall, but the movement is so small that we can't see it. So when do we include a normal force in a free body diagram, and how do we draw it? Here we have two blocks being pushed together by two forces on a surface with no friction. Where do we draw normal forces in the free body diagram for each block? A normal force acts on an object when the object is in contact with a surface or another object. Block A is in contact with the ground, so there must be a normal force on block A from the ground. The normal force is perpendicular to the ground, and it points away from the ground, so it's upwards. For free body diagrams, we usually draw a force vector starting on the edge of the object, so it would look like this. But block A is also in contact with block B, so there must be a normal force on block A from block B. That would point to the left, perpendicular to the surface between blocks A and B, and it points away from block B. Block B is in contact with the ground, so there must be a normal force acting upwards on block B away from the ground. And block B is in contact with block A, so there must be a normal force acting to the right away from block A. There are other forces acting on each block, which we'll cover in other lessons. But these two forces are an equal and opposite pair of forces from Newton's third law, so they must have the same magnitude. And if we drew a free body diagram of the ground, we would see the normal forces acting on the ground from the two blocks. So do we always include a normal force in a free body diagram? Only if the object is in contact with a surface. So if this ball is falling through the air, there would not be a normal force acting on it. And if we have these two blocks attached with a string, there's only a normal force on the block that is in contact with the surface. The force acting on the blocks from the string is a tension force, not a normal force. So that's what a normal force is, but how do we calculate it? Let's look at a few examples. A book with a weight of 20 newtons is sitting at rest on a table. What is the magnitude of the normal force acting on the book from the table? We always start by drawing a free body diagram of the object that we're focusing on. The book has a weight of 20 newtons, which means there's a downwards gravitational force on the book of 20 newtons, which we'll cover in another lesson. Are there any other forces on the book? The book is in contact with the table, so there must be a normal force on the book acting upwards from the table. Now let's establish our coordinate system. We usually say right is the positive x direction, and up is the positive y direction. Now we can write out the equation for Newton's second law, and since we only have vertical forces, we can just write Newton's second law for the y direction. The net force would be the normal force minus the gravitational force of 20 newtons, because we said up is positive and down is negative. The question said that the book is at rest, which means it's not moving, so its acceleration is 0, and we can plug in 0 for ay. The right side just becomes 0, because anything multiplied by 0 is 0. So Newton's second law is saying that the net force on this book is 0 because it's not accelerating. If we rearrange this equation, we find that the normal force acting on the book from the table is 20 newtons, which is the gravitational force. Also, if the question had asked for the normal force acting on the table from the book, it would also be 20 newtons because Newton's third law says that those forces are equal and opposite. So in this example, the normal force is equal in magnitude to the gravitational force. But will that always be the case? This does happen a lot, but only in examples where these are the only two vertical forces on the object and the net force is 0. This is why we can use a scale to measure the weight of an object, which is the gravitational force. The scale measures the normal force, which in this case is equal to the weight of the book. But what would happen if there was another force acting on the book? Let's say a person is pushing down on the book with 5 newtons of force. Now we have to include that force in the free body diagram and the equation for Newton's second law. The net force would be the normal force minus the 20 Newton gravitational force minus the 5 Newton force. It's negative because it's acting downwards, in the same direction as the 20 Newton force. The acceleration is still 0, so now the normal force is equal to the 20 Newton gravitational force plus the 5 Newton force. So the normal force is 25 newtons upwards. If you're wondering why the 5 newtons is added to the 20 newtons and not subtracted, remember that we did plug in negative 5 newtons in the original equation for Newton's second law. But now we've rearranged that equation to solve for the normal force, so this plus sign no longer matches the direction of the 5 Newton force. Let's place a scale between the book and the table. The normal force was 20 newtons before, but if we push the book downwards with an additional 5 newtons of force, the normal force increases by 5 newtons, which is measured by the scale. What if instead of pushing down, we pulled up on the book with 5 newtons of force? That's not enough to overcome the weight, so the book is still in contact with the table, and there's still a normal force. But now, the 5 Newton force is positive in the net force equation, so the normal force is equal to 20 newtons minus 5 newtons, which is 15 newtons. By pulling up on the book, but not enough to lift it off the table, we've decreased the normal force between the table and the book. So the scale measures the normal force, and it only measures the weight if there are no other forces involved. Let's look at one more example where an object is accelerating. A 10 kilogram block and a 6 kilogram block are being pushed by a 30 Newton force on a frictionless surface. If the blocks accelerate at 2 meters per second squared, what is the magnitude of the force exerted on the 6 kilogram block from the 10 kilogram block? Let's draw a free body diagram of the 6 kilogram block. The block is in contact with the ground, so there's an upwards normal force from the ground. There's also a downwards gravitational force. But what horizontal forces do we draw on the 6 kilogram block? Do we draw the 30 Newton force to the right? Well, the 30 Newton force is only acting on the 10 kilogram block, so it would only show up in that free body diagram, but it's not touching the 6 kilogram block. The force that is acting on this block is a normal force from the 10 kilogram block acting to the right, because the blocks are in contact. That's the force we're trying to find. And that force is horizontal, so let's use Newton's second law in the x direction. The net horizontal force is the normal force from the 10 kilogram block, and there are no other horizontal forces because there's no friction. We can plug in 6 kilograms for the mass and 2 meters per second squared for the acceleration because both blocks are accelerating at that rate. That gives us 12 newtons for the magnitude of the normal force acting on the 6 kilogram block from the 10 kilogram block. That's the only horizontal force on the 6 kilogram block, and that's what causes it to accelerate at 2 meters per second squared. Alright, that's it for this video. Thanks for watching, and I'll see you in the next one.